Dear friend, we are here to discuss or we are here to find out a deflection delta B at tip of this beam, which is subjected with a linearly varying load from 0 to W using unit load method. The length of this beam is L, support end is designated with A and free end is with B. Now problem statement is deflection calculation at tip of cantilever beam due to triangular loading. This load is triangular loading. Triangular loading. Edge loading pattern is in triangular fashion. Now we are going to use solve this deflection delta B using unit load method. And general expression for delta is m1 m2 divided by ei into dx integral 0 to L. Here we need to understand what is m1 and m2. The statement for m1 is moment at a section xx from point B. There is a section xx from point B which is at a distance of x from this point B when the beam is loaded with linearly varying load throughout its length. When beam is loaded with linearly varying load, and we need to find out moment mxx. Here it will be m1, and for m2 it is with the statement you can see moment at a section xx, moment at a section xx which is at a distance of x, which is at a section of at a distance of x from point B when beam is loaded with a point load P equal to 1. When this will be acting with a point load P equal to W at the tip of this beam, and for this point load P equal to 1, when if we calculate this moment at a section xx which is at a distance of x from this point B, this moment will also act mxx, but it will be having a value m2 for point load P equal to 1 by removing existing load which was triangular in fashion. Now we have to we can show you with the pictorial representation of m1 and m2 how it will be easy for you to understand, because if we draw in a picture it will be very easy for you to understand rather than for a statement only. The problem statement is this is the beam length L, having length L, in which loading is acting as linearly varying load from 0 to W. Maximum value of this load is W, and this point has been designated as A and this free end is with B, and we are going to calculate a value of moment at section xx which is at a distance of x from point B, and we are going to calculate this moment mxx, so or we can say m1, when this beam is loaded with, when the entire length of this beam is loaded with linearly varying load, or you can say triangular loading. Now for more clarity we can redraw this this beam here, our area of study is to calculate the moment at section x-axis. So we are going to draw this portion with loading pattern. This is the loading pattern up to section x-axis, and this distance is x, and section here is x-axis, where we are going to find moment x-axis. The left part of this section we can show in dotted line so that it will represent the same beam having total length L, and maximum value of loading, triangular loading, is W, which is acting at its support. And now designate the support point is A and free end is B, and let us suppose this point is C. To calculate moment at section axis, we need to find total loading in this triangular portion, this portion. Suppose we can designate this point and this point here, it is D, and this point is E, and we need to find area of this loading, that you can say area of the hashed portion, area of the hashed portion, hashed portion of loading diagram. Area of the hashed portion of this loading diagram will give the total load acting from point B to section XX. Total load through this length of for a length of beam which is X will have a total load equal to area of this loading pattern, and total load multiplying with the centroid of this loading pattern will give moment at section XX. Now, so in order to find the area of this loading pattern, we have this length X, but we don't know about this length. We don't know about this length. Suppose this length is Y. ED equal to Y equal to what? We need to calculate this length ED equal to Y. From similar triangle we can calculate it very easily. This is forming a two triangle. There is one triangle from A to ABC and another triangle EDB. We can draw it here. There is one triangle here. This point is A, this point is B, and this point is C. This value is W, this length is L. There is another triangle up to length X, which is here. This point is D, this point is B, and this point is E. Triangle 1, triangle 2, and this DB distance will be X, this distance X, and we need to find this value Y, ED equal to Y. From similar triangle rule, from similar triangle, W divided by L will be equal to Y divided by X. Therefore, Y will be equal to W by L into X. Now value for loading at section XX, that is Y, is calculated as here, this one, W divided by L into X. This is the calculated value for Y. Now Now, in order to find the moment m1 at section xx, we can redraw the triangular loading edge. This is our loading pattern up to portion. This is our length x, and you can say this is section x where we need to find a moment xx. Now we can draw the left part of this one for our understanding. This is our length, but our area of study will be this one. This is the loading pattern up to this is point A, this is point B, this is point C, this is D, and this is E. Our area of study is up to B to D. We need to find total load of this triangular loading from B to D and centroid of this triangle, so that we can find moment mx, which is m1. Now the value ed, or you can say this value was y1, which was calculated as here. This value we have calculated here, w divided by L into x. So y equal to w divided by L into x. This is the value calculated for ED. So area of this triangle will give total load acting for the length x. So total load will be area of the triangle E D B EBD loading pattern. Now maximum loading pattern in this triangle is y equal to w divided by Lx, and base is x, so area will be half base is x multiplying with y, and y value is this one, so we can say half into x multiplying with w divided by L into x, this value. So total load will be wx square divided by twice L. This is the total load. Now centroid of this triangular loading from B to D will be, this is our triangular loading, which is our area of study. To find out its centroid, we are going to find moment at xx. So total load will be acting, this is the total load will be acting at centroid of this triangle. This is the total load. Total load is nothing but wx square divided by twice L. This is the total load. But it is acting at a distance of x by 3. You can say x by 3 as this length is x, and this point is D, this point is B, and this point is E, and total load wx square by twice L is acting at a distance of x by 3 from section xx. This is section xx. So total load multiplying with the distance will give moment mxx at section xx. So mxx will be, or you can say m1 will be total load multiplying with the distance w x square divided by twice L multiplying with distance x by 2, no, x by 3 will give moment at section xx. The moment value will be w x cube divided by 6L. So calculated moment is moment mxx, or you can say m1 is wx cube divided by 6L. This is the calculated moment for m1. Now second part is to calculate m2, so that we can put m1 and m2 for the general expression for calculation of deflection at point B using unit load method. Now in this part we are going to find calculation for m2. Calculation for m2. Calculation for m2. Now the loading pattern is, for the statement of m2, it will be something like this. The length of this beam will be L, and it is acting at tip of this beam, and value of this load will be P, which is equal to 1, and we need to find moment at a section xx, which is at a distance of x by x, which at a distance of x from this point B. This point is B, tip of this beam, and this point is A. So it's very easy to calculate the moment. Load multiplying with distance will give the moment. So m2 equal to, load is P equal to 1, multiplying this load with x. So 1 into x will give x. Therefore m we have calculated here, m1 we have calculated here. This value is, this is our mxx or m1. This value is our calculation for m1, and m2 is here x. So we can summary m1 equal to wx cube divided by 6L, wx cube divided by 6L, and m2 equal to this value x. Therefore from the expression of deflection delta using unit load method, it is calculated as m1 m2 dx divided by ei integral 0 to L. Now in place of m1 we can put this value, in place of m2 we can put this value, and integrating whole expression from 0 to L, we will find deflection delta at point B, at the tip of this beam. So we can take 0 to L, m1 wx cube divided by 6L, and in place of m2 we can take x into dx. So and this part is divided by ei. Taking 6L divided by ei outside, 1 w6L divided by w6L and ei, everything will be outside, as these are the constants from this integral. We can rewrite this one, w divided by 6 ei L, and x cube x multiply, it will be 0 to L x to the power 4 to dx. This will be w6 ei L multiplying x to the power 4 will have an integral value of x to the power 5 divided by 5 is value ranging from 0 to L. Therefore, delta will be W divided by 6 EIL multiplying L to the power 5 divided by 5. Now L 5 cancel, it will have a value of L to the power 4. So overall value will be W L to the power 4 divided by 6 multiplying with 5, it will 30 EI. Therefore delta will be, that is delta B, deflection at tip of this beam will be W L to the power 4 divided by 30 EI. This is the calculated value for deflection at point B for beam, cantilever beam, which is subjected with triangular loading. In our next lecture, in next two lecture, I will solve same problem, same beam subjected with triangular loading and having length L, but it will be solved with conjugate beam method and moment area method, and you will find deflection calculated as same, so that you will be expert for the calculation of deflections using any method, moment area method, unit load method, strain energy method, or conjugate beam method. Whatever method is convenient to you, you can adopt any of any of this method, not an issue. Now I would like to summarize this one, that for the calculation of deflections we generally find two value m1 and then m2, and there is a general expression of m1 and m2 using moment unit load method, and putting m1 and m2 in this expression and just doing integral for this expression, we find a deflection. Dear friend, I hope you find this lecture very interesting for you, but if you find any kind of doubt or any issue regarding the solution of this problem, you can write in comment box. I will surely answer to you. And please keep watching, keep sharing to your friends and colleagues, and please subscribe my channel, MSA Structural Engineers. Thank you so much for watching.